Hello guys, here is Ahmed and here is a new video on the optimization course. In this video we will continue about mathematical revision. We will revise some mathematical notions about derivatives and gradients. The derivative f prime of x of a function f of a single variable x is the rate at which the value of f changes at x. The function here is drawn in black. The derivative of this function f at x is the slope of the tangent line. Here the tangent line is drawn in blue. Now if we take these three figures, here the tangent line is obtained by joining points with sufficiently small step differences. So here, as you see, derivatives in general, we consider differential and continuous functions of n variables x from x1 to xn. The function is denoted by f of x or f of x1 until xn. Changing one of the parameters affects the value of f. The derivative with respect to the ith parameter tells us how sensitive the function is with respect to that parameter. Derivative approximation, the first point we will talk about here. So the first order derivatives are obtained by perturbing the parameters one at a time and determining the corresponding relative change of the function. It is denoted by this variable. Partial derivative of f with respect to xi is the limit when delta xi goes to 0 of the function where we will perturb, find the difference between f. So this is the definition of the derivative with respect to the ith parameter of the function. The perturbation should be as small as possible. Using forward difference formula, the derivative can be approximated by this expression where we make the difference of f and we perturb with respect to xi divided by delta xi. So this must be finite small perturbation. This is called FFD, forward finite difference. We can also use backward finite difference to calculate an approximation of the derivative. It can be given by this expression. And also we can use central finite difference, and it is given, to find the derivative, it is given by this expression. Here we add delta x and we subtract delta xi, and we have a distance 2 delta xi. Each formula has its advantages. FFD requires one extra function evaluation in the forward direction. BFD is the same. It requires one extra function evaluation, but in the backward direction. and CFD is the average of both FFD and BFD approximations. It will give better accuracy of the calculation. Now we will talk about the gradient of a function. So derivatives in multiple dimensions. So the gradient is the generalization of the derivative to multivariate function or function with multiple variables. It captures the local slope of the function, allowing us to predict the effect of taking a small step from a point in any direction, as we see in the figure. The gradient points in the direction of the steepest ascent, so we're going up, of the tangent hyperplane. So this is the hyperplane we see for this function. What is a hyperplane? In an n-dimensional space, it is the set of points that satisfies this expression w1x1 plus plus equal b, where w is a vector and b is a scalar. It has n-1 dimensions. So here, each component of the gradient defines a local tangent line. These tangent lines define the local tangent hyperplane. The gradient vector points in the direction of the greatest increase. So what is the gradient? The gradient, which is denoted by nabla f of x, is the column vector of its derivatives relative to all parameters. So nabla f is the partial derivative with respect to f, with respect to x1, to the x2, and so on. So the gradient varies in general from one point in the parameter space to another. A differentiable nonlinear function can be approximated within a small neighborhood of a point x by the first order Taylor expansion. So f of x plus delta x will be equal to f of x0 plus transpose the gradient times delta x. Which is a vector, so we can develop it like this. And delta x is the difference between x and x0. It is a vector, so we have delta x in one direction, x1, x2, and xn. These partial derivatives are evaluated at the point x0. This linearization approximates the original nonlinear function only over a small neighborhood of the point x0. Let us take an example to be more clear. So we have this function. We have two variables, x1 and x2, and our objective is to find the gradient at a point given 1, 1. So the solution for this example, we will calculate the gradient, so the partial derivative with respect to x1 and x2. So we can calculate it easily. We will get this expression. And at the point x0, 1, 1, we replace 1 and 1, and we find that the gradient is -3, -1. Let us apply FFD, BFD, and CFD approximations on this function. So with delta x equals 0.05. So f at 1, 1 will be equal to 0. F of delta x, f of x0 plus the first delta will be like this, with E1 is 1, 0 and E2, 0, 1. F of x0 plus delta x E1 can be calculated. So I will put all the calculation here. So in one direction and in another direction, we will get these values. Yeah, here I have to put minus. So plus minus. And we will get these values. So we have to write all of these things. So to find the FFD. So FFD is the difference in the forward direction in the direction of x1 and x2 over delta x. I am copying only the numerical values, and we will get this value of the gradient, which is a little bit far from the analytical solution. For the PFD in the backward direction, we also do the same thing, and we calculate everything here, and we will get these values. So it is -3 and -1.05. For the central finite difference, so we have 2 delta x. So we calculate everything here, and we will get these values. So I am copying everything calculated previously. And you see it is near the analytical value, -3 and -1. So this approximation is identical to the analytical solution or gradient. So here I will explain what is the Jacobian and how to calculate the Jacobian. So the Jacobian, so take a vector of m functions, f of x, f1, f until fm, and every function has its gradient with respect to the parameters x. So the Jacobian is the gradient of each function of this vector. So we can write it like this. So we have a n by m matrix. So the gradient of the partial derivative of f with respect to all the x. So it is a rectangular matrix of m rows and n columns. The linearization can be generalized for the vector function f to get the expansion f of x plus delta x is approximately f of x plus the Jacobian delta x. Let us take the example of this function with 3 variables x1, x2, and x3, and we want to find the Jacobian of this function at x0, 2, 1, 1. So use the Jacobian to estimate the value of this vector function at the point x1, 2.1, 1.2, and 0.9. The solution, so the Jacobian of x, as we know, we have 2 variables, so it is the gradient of f1 and f2. We can calculate it easily here. At the point x0, we replace the value, so we get the Jacobian equal 12, 30, 12, 0 minus 2. Using the formula, we know the Jacobian and we know delta x. So f of x1 will be f of x0 plus the Jacobian as x0, x1 minus x0. We put everything exactly. 1, 2, 2, yes. So the function at x1 will be equal to this value. The exact value of the function at the new point f of x1 is 14.958 and 7.46. So we see that we have a difference between the exact value and the approximation. The accuracy of the linearization continues to deteriorate as we move further from the expansion point, as expected. Now we will talk about the Hessian, or the second derivative. Second order derivatives, they, by definition, are the rate of change of the first order derivatives for a function f of x with n parameters. The mixed second order derivative with respect to the ith and jth parameter is given by this expression. So it is the limit of the difference here of the first order derivative So here we write the formula over delta xj. All the second order derivatives of a function f of x are combined in the compact Hessian matrix H. So H, I will write the expression here of the Hessian. So we'll derive second order derivative with respect to x1, to x2, to xn, and so on. So it is a symmetric matrix because the order of the differentiation does not make a difference. Let us take an example to see how to find the Hessian of a function. So we have this quadratic function with x1, x2, and x3. And our objective is to find the gradient and the Hessian at a point x0 given 1, -1, and 1. The solution, so nabla f of x, we make the gradient, derive with respect to x1, with respect to x2, and to x3. We replace the point, and we get this gradient. For the Hessian, so it is the derivative of the gradient, so we have 6, 2, 1, 2, 5, 2, 1, 2, and 4. In this case, the Hessian does not change with the parameters as the function is quadratic. Let us see how to apply this in Matlab. So here I will start with some management function, clear, CLC, compact format, and I will stop the warning. I will use the symbolic toolbox of Matlab. So we use SAMs. So x1, x2, and x3 are symbolic objects. I will write the functions that we used in this video. So this is f1, f2, and the last function f3. And in z1, z2, z3, I put the point, the initial point that we want to use to calculate the different gradients and derivatives. So let us execute this. So clear. Then I will execute the second section. So we have, as you see, the function f1, f2, and f3. So f3, it is written, so 3x1 square, and so on. Now we can try to display the variables with this function whose. So as you see, we have f1, f2, f3, and the variables, and z1, z2, z3. So as you see, f1 and f2 and f3 are also symbolic variables because they use symbolic variables x. We'll print this separation derivatives. We're using fprintf. Then we will try to find the first derivative of f of 1 with respect to x1 and the first derivative of f1 with respect to x2 using diff. And as you see, we get the gradient of f of 1 as we calculated manually, but here we use the symbolic toolbox of Matlab, the symbolic calculation, to get the gradient. If we want to find the Jacobian, we use the keyword or the function name Jacobian. We put the name of the function. Okay. And if we want to evaluate the function at a certain point, we will substitute the symbolic variables by numerical values stored here in Z1, for example. So we can find the first derivative with respect to x1, with respect to x2, and we can find also replace the gradient. So run, and as you see, we get the values that we calculated previously by hand. So this is useful if we have a complicated function. We can use the symbolic toolbox and then substitute the values. Here, for f2, we want to find the Jacobian. We have three variables, x1, x2, and x3. So I will run the section. And as you see, we get the Jacobian of the function. And if I want to evaluate the function, I substitute using subs, and I put the value. It will give the same value, 1230. If we want to find the Hessian, we have several methods. We can find the Jacobian of the function, and the Hessian will be the Jacobian of the Jacobian. Or we can directly use the function Hessian in the symbolic toolbox, and as you see, it will give me the same value. So here, Hessian A and B are the same. For Julia, I will show you also what we can do in Julia. So here I will use the symbolic engine in Julia. I will create f1. I will create f2, a generic function. I can find the first derivative, as you see with diff. I can find the second derivative. I can also find the gradient as in Matlab. I can also use the diff function with the dot function, which is to broadcast the computation. So as you see here, we calculate the gradient. I also have to make the transpose to get the gradient in the correct way, as you see of this function. I can substitute the value 211 by using subs. So as you see, we get the same value, 12.3 minus 2. If I want, I also can use forward diff to find the calculation of the gradient and the Hessian in another way. As you see, I apply this for the third function, f3. So I use here brackets, and I will replace x equal 1, minus 1, and 1. So by running this code, Julia code, I can find the gradient of f3 at the point 1 minus 1, 1, and the Hessian of the same function at this value. As you see, the last result is h, and we get the same result as in Matlab. Thank you for watching. I hope that you enjoyed this video, and for more information you can see the description of this video. Bye bye.